For cation to occupy a trigonal sides of an ion, R positive and R negative should be smaller than 0.155. Only B3 positive ions can fit in such a small sites in its oxide B2O3. Radius ratio for tetrahedral side. A tetrahedral side is cubic is shown by placing sphere at the alternate corners as shown in figure. A stable tetrahedral arrangement has 4 anions at the corner touching each other and also cation placed at the center. However, for simplicity, the cation and anion are shown distant circles. Actually, the cation and anions are touching one another. Suppose A is the length of each sides of cube. R positive and R negative are the radii of the cation and anion respectively. In the figure, AC is the face of diagonal in triangle ABC. AC square is equals to AB square plus BC square. AC is equals to under the root A square plus A square is equals to 2A. There are two tetrahedral sides per atom in a closed packed lattice. This means that there are two tetrahedral sides available for every S2 negative ion. Since only half of these are occupied by Zn plus 2 ions and the stoichiometry of the compound is 1:1. In the structure, each S2 negative ion is surrounded by Zn plus 2 ions which are dispersed towards the corner of regular tetrahedron. Similarly, Zn plus 2 ions surrounded by 4 S2 negative ions such when ions and all 1 S2 negative ions shown in figure. Therefore, the coordination number of Zn plus 2 and S2 negative ions is Woodside structure are 4:4. Basic difference between zinc blende and Woodside structure. It will be noted that the basic difference between zinc blende and Woodside structure is that the zinc blende structure and the sulfide ions are arranged in CP type packing, whereas the Woodside structure they are arranged in SCP type of packing. Structure of cesium chloride. The unit cell of cesium chloride is shown in figure 19. In this structure, cesium ions are represented by solid circle whereas the chloride ions are represented by hollow circle. Silent feature of cesium chloride structure are as follows. The chlorine ions are arranged in simple cubic arrangement. In this arrangement, the chlorine ions are present at all the corners of the cube. Cesium ions occupy cubic sides. Cesium positive ions represent at the body center of the cubes. It is clear that there are 8 chlorine ions at the corner of the cube. Each ion at the corner is shared between 8 unit cell and it contributes per unit cell 1/8. Therefore, 8 chlorine ions at the corner 8 into 8 1/8 is equals to 1 chlorine ion per unit cell. Thus for cation to occupy the trigonal sides of the anions, the R positive and R negative should not be smaller than 0.155. Only B3 positive ions can fit in such a small sites in its oxide B2O3. Radius ratio for tetrahedral sides. Tetrahedral side in a cube is shown by placing sphere. The alternate corners are shown in figure. The stable tetrahedral arrangement has 4 anions at the corner touching each other and they also cation placed at the center. However, for simplicity, the cation and anions are shown by distant circles. Actual, the cation and anions are one another. An actual arrangement, cation and anions are one another. Suppose the distant circles actually the cation and anion are touching one another. Suppose the anions are present at alternate corners of the cube and the cation occupies tetrahedral side. Suppose A is the length of each side of cube and R positive and are the radii of the cation and anion. In figure, AC is the face diagonal in triangle ABC. AC square is equals to AB square plus BC square. AC is equals to under the root AB square plus BC square equals to root 2A. Radius ratio for cubic sides. A cubic side is shown in figure. The sphere are not shown touching one another. For the sides of the simplicity, suppose the length of each side of cube is A and R positive and R negative, the radii of cation and anion respectively. Thus, limiting R positive and R negative ratio of cubic sides are 0.732. Lattice defect. Ionic crystal well defined order to constituent ions and ionic crystal which has a same unit cell containing the same lattice point throughout the whole crystal is known as ideal crystal. However, such ideal crystal exists only at absolute zero temperature. At any temperature above 0 degree Kelvin, the crystal has some departure from complete ordered arrangement. Any derivation derivation from completely ordered element in a crystal constituent a disordered or a defect. The crystal may have additional defect due to presence of some impurities, and the term disorder or imperfection is generally used to denote departure from perfectly ordered states of constituent of the particles. This imperfection will not be change the properties of the crystal but also give rise to a new property. There are commonly two types of defects in stoichiometric crystal, defects in non-stoichiometric crystal. Defects in stoichiometric crystal. Stoichiometric compounds are those in which the number of positive and negative ions are exactly in the ratio indicated by the chemical formula. For simplicity, we can consider the compounds of type A, B have equal number of A positive and B negative ions. The defect in these types of compounds are called stoichiometric defect. In this compound, two types of defect are generally observed. These are Schottky-Frankel. Schottky defect. This defect was discovered by German scientist Schottky in 1930. It arises if some of the atoms or ions are missing from their normal site. The lattice sites were unoccupied are called lattice sites, lattice vacancy or holes. Since the crystals to remain electrically neutral, equal number of cation and anions are missing. The ideal AB crystal is shown in figure. The existence of two holes, one due to missing of cation and other due to missing of anion. Condition causing Schottky defect: high coordination number and ions of almost similar size. Coordination. Frankel defect. The defect was discovered by Russian scientist Frankel in 1926. It arises when an ion is missing from its normal position and occupy interstitial sites between the lattice point. The existence of one hole due to missing of cation from its normal position occupying an interstitial position is shown in figure 3.1. In this case also, the crystal remains electrically neutral because the number of anion and cation remain the same. Condition causing Frankel defect. This defect generally occur in compound in which coordination number is low and anion are much larger than in size of cation. In pure alkali metal halides, these defects are not very common because the ions cannot get interstitial position due to their large size. This defect can be found in silver halides such as AgCl, Ag, or Agi. Because of small size of Ag positive ions, it can be going to the interstitial side. We observe the vacancy or holes are present in crystal with Schottky as well as Frankel defect, but the formula leads to decrease in overall density of the substance, but later does not. Certain ionic solids such as AgBr, both Schottky and Frankel defect occur. Consequences of Schottky and Frankel defect: because of presence of this defect, the electrical conductivity of crystal increases. When the electric field is applied, nearby ions moving from its lattice sites occupy a hole and another nearby ions move into it, and so on. This process continues and the hole thereby moves from one end to another, and thus it conducts electrical across the whole of the crystal. Due to presence of holes in the crystal, its density decreases. However, it may be noted that density decreases only for crystal having Schottky defect. The presence of holes also decreases the lattice energy and the stability of crystal. Presence of too many holes may cause partially collapse of the lattice. The closeness of similar charges in Frankel defect tends to increase the dielectric constant of crystal. Difference between Schottky and Frankel defect: it is produced because of missing of same number of cation and anion from their normal crystal sites. It is produced when the some atoms or ions displaced from their normal position sites and occupy interstitial site. The presence of Schottky defect lower the density of crystal. It does not affect the density of crystal. It is generally shown by ionic solid having high coordination number and in which cation and anion are equal in size. It generally occur when low coordination number and large difference between the size of cation and anion. Defects in non-stoichiometric crystal. Defects in non-stoichiometric crystal: the compounds in which the ratio of positive and negative ions present in the compound differ from that of required by ideal chemical formula of the compound are called non-stoichiometric compound. This defect is compounds are called non-stoichiometric defects. Vanadium oxide For example, has the formula VOX, where X lies between 0.6 to 1.3. Similarly, iron 2 oxide sample contain more oxygen atom than iron atom, while the sample of zinc oxide usually has excess zinc atom than oxygen atom. Iron atom, while sample of zinc oxide usually excess zinc atom than oxygen atom. However, it may be noted that in each case the electrical neutrality of crystal is maintained. There are two type of depending upon their positive ion in excess or negative ions in excess. They are also known as metal excess or metal deficiency defect. Metal excess, in this defect, positive ions are in excess. They arise in two ways: an ion vacancy. Negative ions may be missing from their lattice site, leaving holes in which the electron remain entrapped to maintain the electric neutrality. There is excess of positive metal ions, although the crystal as a whole in electrical neutrality. Example, in alkali metal halides, an ion vacancy are produced when alkali metal halides crystal are heated in atmosphere of alkali metal vapor. The metal atoms get deposited on the surface of alkali metal halides crystal. Halides ion moves into the surface and combine with metal atom. The electron into the surface and combine with metal atom. The electron thus produced by the ionization of metal atom diffuses into the crystal and get trapped at the anion vacancy. The electron trapped in an ion vacancy are referred to as a F center. This gives rise very interesting property. For example, the excess of potassium KCl making the crystal appear violet. Excess lithium make the crystal appear pink. KCl. Excess cation occupy interstitial sites. In this case, there are extra positive ions occupy the interstitial sites. Thus, electrons in another sites to maintain electrical neutrality. Defect may be visualized as the loss of non-metal atom which leave their electron behind. The excess metal ions occupy interstitial position. This type of defect in the crystal which are likely developed by Frankel defect. Consequences of metal excess defect. The crystal with which metal excess defect is conducted due to presence of free electron. However, the conductivity is very low because of the number of defect, and therefore the number of free electron is very small. Because of low conductivity as compared to conductivity of metal, there are also called semiconductor. These compounds are also called n-type semiconductor since the current is carried by the electron in the normal way. The crystal in metal excess defect are generally colored. For example, non-stoichiometric sodium chloride is yellow, non-stoichiometric potassium chloride is violet. Metal deficiency defect. These contain less number of positive ions and then negative ions. They arise due to one ways cation vacancy. They arise due to two ways cation vacancy. In some way, positive ions may be missing from their lattice sites, and the negative charge may be balanced by the electrons to acquiring two positive charges instead of one. This is shown. This type of defect is possible in metal which have variable oxidation states such as iron sulfide, such as iron pyrites. For two iron Fe+2 ions and Fe+3 ions are present. About the lattice energy of ionic crystal. The stability of ionic crystal is determined in terms of their lattice energy. The lattice energy is defined as the amount of energy released when 1 mole of ion crystal is formed from its constituent ions in the gaseous state. The formation of 1 mole of ionic solid from its constituent gaseous ions may be represented as mg positive plus may x negative mgx delta h is equals to my lattice energy minus u. The lattice energy is expressed by u. The negative sign is used because energy is released in the process. Since the ionic bond is formed as a consequence of electrostatic attraction between the positive charge ions, there is considerable decrease of potential energy of the system. As a result, if 1 mole of solid ionic compound is broken into its constituent gaseous ions, energy will be needed which will numerically equal to the lattice energy. In this case, U has negative positive signs because energy is absorbed in the process. It is obvious that if the compound is stable, a large amount of energy will be needed. This means the higher the lattice energy of an ionic compound, the greater will be stability. Lattice energy of some ionic compounds are given in table 3. It is evident from the above table that the lattice energy of an ionic solids are quite high because of strong electrostatic attraction between the positive charge ions present in the solid. Since Coulombic force of attraction vary directly as the product of charges, it follows that the higher the valency of the ions, greater would be the lattice energy of the ionic solid. Thus, the lattice energy increases as we move from univalent ionic solid to bivalent ionic solid, then to bivalent ionic solid. Born-Haber cycle for lattice energy. Born-Haber produced a method to relate lattice energy of ionic crystal thermodynamic data. This is known as Born-Haber cycle. We have learned the formation of bond take place only if the decrease of energy. As example, let us consider the energy of charge during formation of sodium chloride. For metallic sodium and chloride gas, formation of Born-Haber cycle, Na plus half Cl to NaCl. The overall process is to take place the following step: conversion of metallic solid into gaseous solid. The sodium atom can lose its electron only in gaseous state and has to be sublimated. The energy required for conversion of 1 mole of metallic solid into gaseous solid is known as sublimation energy. It is represented as S. Dissociation of chlorine molecules into chlorine atom. Dissociation of chlorine molecules into chlorine atom. Each chlorine molecule consists of 2 atoms of chlorine. The amount of energy required to conversion of gaseous chlorine molecules into atom is known as dissociation energy. The energy required for producing 1 mole of gaseous chlorine atom is d by 2. Third, for conversion of gaseous sodium atom into sodium ion, the amount of energy required to convert 1 mole of gaseous sodium atom into the sodium ion is known as ionization energy. Conversion of gaseous chlorine atom into gaseous chloride ion. The amount of energy is released during the conversion of 1 mole of gaseous chlorine atom chloride ion is known as electron affinity. Combination of opposite charge ions to form a solid crystal. The opposite charge Na positive and Cl negative attract each other to form NaCl crystal. This leads to release of energy, and the amount of energy released when 1 mole of solid compound is obtained from gaseous ion to a positive charge is called lattice energy. It is denoted by U0. The overall energy change may be expressed as the heat change for the reaction formation. It may be denoted as delta HF. According to Hesse's laws, the heat of formation of 1 mole of sodium chloride should be same respectively. The fact whether it takes place directly in one step or through a number of steps is in the above. Thus, the lattice can be calculated knowing the value of different quantities. While using the above relation for the lattice, a special care should be taken. The sign of various quantities. A positive sign is used for energy absorbed and negative sign is used for energy released. Application for Born-Haber cycle. The Born-Haber cycle has been used for calculation of many properties. Some of the important uses are given below. Calculation of heat of formation. Heat of formation of unknown compound can be easily calculated by making a Born-Haber cycle. For example, for NaCl type crystal, heat of formation is given as similarly for crystal MgF2, the heat of formation L about the stability of compound. If the heat of formation is out of to be negative, the reaction is exothermic. The compound formed will be stable. On other hand, if the heat of formation come out to be positive, the reaction is endothermic and the compound will the formation of compound highly unfavorable. From heat of formation, it can be explained by why NaCl2 is not formed. Through it expected a higher lattice energy than NaCl. The heat of formation of NaCl2 Born-Haber cycle is out to be highly positive. Calculation of electron affinity. The Born-Haber cycle can be used for calculation of electron affinities of some elements which are otherwise very difficult to measure. Heat of formation of a compound may be expressed as it may be rearranged as this in the case as delta H, D or IE as experimentally determined, and lattice energy U may be calculated by using Born-Haber equation. Using above equation, the electron affinity may be calculated. Estimation of proton affinities. The Born-Haber cycle can also be used to calculate the proton affinities of different bases. The electron affinity of a species X is defined as the energy released in the reaction Xg plus del H positive G makes HX positive. For example, the proton affinity of ammonia may be expressed as This can be easily calculated by considering the following Born-Haber cycle. NH3 plus MeHCl make NH4 positive plus MeCl. According to Born-Haber cycle, delta HF is equals to D plus Me ionization energy plus electron affinity plus Me Pa plus Me U. Knowing the value of delta HF, D, Ia, Ea, U naught, we can easily calculate proton affinity. For the reaction NH3 and HCl, the following data. The proton affinity of ammonia is this, and the negative value indicates the reaction is favorable and the ammonia has good energy to accept the protons. Melting point of CuCl is 7.705 Kelvin, then that of NaCl is 1073 Kelvin. Similarly, Ca plus 2 and Hg plus 2 have almost similar ionic radii, but Hg plus 2 has 18 electron shells, whereas Ca plus 2 has 8 electron shell. Therefore, Hg plus 2 is more polarizing than Ca plus 2 and its compounds are more covalent. For example, melting point of HgCl2 is 549 Kelvin, while the CaCl2 is 1065 Kelvin. We have already explained the low solubility of silver halides in water in comparison to sodium halide. The silver halide acquires covalent character because of greater polarizing power to Ag positive, and thus, according to Fazan's rule, the covalent character will be favored by the small size of cations, larger size of anion, high charge of cation, and the cation having 18 electron shells. Thank you. Chapter Ionic Solid Physical Chemistry, Inorganic Chemistry completed.